So far for the prediction of hydrate formation condition, we have learned about the first technique or the first method, which is the what we call the Katz gas gravity method. And now we're gonna look at the other method, which is specifically, or we're gonna list four methods that we're gonna discuss, which is Katz equilibrium constant, the Bailey and Witcher charts, and equation of states, and Campbell empirical method as well. I think we're gonna cover them briefly, not in details. We're gonna show you how they were derived and what are the main or what is the method behind them, or can you use them. The first method that we're gonna look at is what we call the K-factor method, which is the Katz equilibrium constant, and it's specifically, and if you still remember it, because the Katz method also we have seen it graphically, the first method, which is based on the specific gravity, and it was also applied for sweet gas. Here similar scenario. Here Katz equilibrium constant, or the K-factor method developed by Katz, put a set or a value for something called KVS, which is very similar to what we call the equilibrium constant for the vapor solid equilibrium, where you deal with the with the hydrate material as a solid material that include also gas and include also liquid. But the Katz method has good prediction for sweet gases or for gases that has small amount of CO2 and H2S, and also has relatively low pressure up to 7 megapascal. And the method is based on the what we call the vapor solid equilibrium constant, which is again defined as you have seen it before in thermodynamic as KVS, which is the equilibrium constant for vapor solid, as Y divided by QS, where Y is the mole fraction of the hydrocarbons in the gaseous phase on a water-free basis. Means that you do not include water in your calculation, because you are dealing here with two phases. You are dealing with the vapor, which is the gaseous phase, and you are dealing with the solid, which is again the crystalline or the water, but it's in the solid phase, not in the liquid phase. And XS is the mole fraction of the hydrocarbon in the solid, again excluding the water content as well. Now for the Katz method, as we explained earlier, or what we call the Katz equilibrium constant, which is KVS, they list or the value for K, or the KVS, which we called before as KVS, which is the equilibrium constant for vapor solid, V vapor is S solid, and where the applicable K values for the hydrate forming molecules for different hydrocarbon molecules are shown in different figures, from figure 220 to 23 to figure 2029. So all these figures will represent the K value, or give you an idea about how much is the K value for certain compound, for example CH4 for ethane, for propane, at specific temperature and pressure as well. And this is available in the GBSA engineering data book. I'm going to represent in the next slide, I'm going to present an example of this chart, or the Katz equilibrium chart, or the value, how you can obtain the K value or the equilibrium constant value from the chart for methane specifically. Also Robinson also added to this method where he can also find, for example, the K values for the H2S on a separate chart as well. And as we explained earlier, or as we agreed earlier, that normal butane normally will not form by itself hydrate, but it will contribute to the formation of the hydrate. And this method should not be used for pure components or for mixture that contains larger amount of H2S, more than 5%, which is again get back to the point where it's applicable. Once you see Katz equilibrium method or Katz specific gravity method, both are based on the fact that you are dealing with sweet gas, not sour gas. So this is one of the charts that we were talking about. We said that in the GBSA book, from chart 2023 to chart 2029. Here is we are dealing with, or we are showing the first chart, which is 2023, which is specifically for methane only. And you can see that this is the what we call the Katz equilibrium constant. In the x-axis you have the temperature in Fahrenheit. In the y-axis you have the K value, or the equilibrium constant for the vapor solid phase, and you have different temperature range, or sorry, different pressure range in the PSI absolute. Okay, so you can simply say that, for example, if you have the temperature around 40 degrees Fahrenheit, okay, and the pressure, let's say that the pressure is approximately 250, for example, this means that your KVS value would be approximately equal to 2, and this is again for methane. So when you see the KVS method or the equilibrium constant method or the K factor method, this is again what we call the Katz equilibrium method, and this is again for a prediction of different or the hydrate formation condition for different component. So for the again for the Katz equilibrium constant or the K factor factor method, you're gonna apply the same method that you have dealt before, you have used before, and for the dew point calculation, where you're gonna have an objective function and the summation of this objective function, which is the summation of yi, where yi, as we explained earlier, is the mole fraction of the hydrocarbon in the gaseous phase excluding the water, divided by the k, which is the equilibrium constant. The summation for all the components will be equal to 1. And as a rule of thumb or as a guideline, you can say that if you have N-butane in your gas mixture, you're going to use the K value for N-butane similar to the ethane, because you don't have K value for N-butane in this case. And if you have nitrogen and heavy hydrocarbons greater than NC4, which is N-butane, you take K to be approximately equal to infinity value. So the first step in your calculation is basically what we called before as the flash calculation in thermodynamic, where the temperature, pressure, and the composition will be the input that you're going to use, and in order to obtain what we call the objective function to be equal to 0 in this case, where Z or Zi stands for the mole fraction of each component in the feed, KVSI is the K value or the equilibrium constant for component I, and as we mentioned earlier, for heavy hydrocarbon and nitrogen we use it to be equal to infinity, and V is the vapor fraction. And as a result, you need to do what we call iteration. So iteration approach is required in this case to solve for the vapor fraction phase. For example, to calculate how much is the V value, or what we called before as the fraction of the gases of the hydrocarbon in the gaseous phase. In order to calculate or to find, so in order to calculate or find V, you need to do what we call the iteration, where you set the objective function to be equal to 0 and you try solving this approach. But again, we are not going to be using this in more details. It's more to know the method itself. You can go and read more about it, but for the purpose of this course, we're gonna mainly deal with the chart methods. Most of the time we're gonna deal with the chart method, but it's good for us to know how or what other methods are dealing with, or what other methods are applied or used. So the first step, as we explained earlier, is to calculate or to find how much is the V, or the vapor phase fraction of that. Once you calculate, or once you specify how much is the vapor phase fraction from that point where you put an objective function to be equal to 0, knowing what is the temperature, what's the pressure, what's the major composition of each compound, then you can calculate how much is the vapor phase composition, or what will be the YI, or the vapor phase composition, because this is will be given, and this is given, and this is given, and now you calculated V from the previous step, so you can calculate how much is YI. So if you calculate YI, then you can calculate how much is SI, which is the solid composition, which is defined as the yi divided by the k value for that specific component. And then from that point of view, you start to calculate the what we call the third type, or the second type of calculation, which is again basically similar to the dew point calculation, where you set an objective function to be equal to 1 in terms of yi divided by k vsi. So how this can be done? So let's imagine the situation that you know how much is the, for example, the pressure that you have. So if you know the pressure, how much is the pressure you have, and you know that you need to obtain KVS. So how do you obtain KVS? You obtain KVS from the chart. The chart has temperature and has certain pressure. So if you know the pressure, then you can assume a specific temperature, and then you assume the specific temperature, then you do the calculation and you do the summation, and you see is it equal to 1 or not. If it's not equal to 1, then you take another value for temperature till you reach the point where you get the summation equal to 1. If you have the opposite scenario where you know the temperature and you need to know the pressure, you do the same thing. You assume a specific value for the pressure and you start to calculate the summation for, you know the temperature, then you assume a value for the pressure, and from this value for pressure you assume that okay, you have T and you assume value for pressure, you calculate how much is KVS, and then you start to look at the summation. You start to take the summation. If the summation is equal to 1, then it's ready. The answer is correct. If the summation is not equal to 1, then you will assume another value for the pressure, for example, and take another value for KVS for each component, and then you do the calculation based on that till you reach to the point where you have the summation of the mole fraction divided by the K, or the equilibrium constant, equal to 1 for all the component. So this is how you do it by iteration approach. Now the second method, which is called the Trickle-Campbell method. Trickle-Campbell method come after the what we call the Katz method, because Katz method is pressure limited one, or pressure limited approach, and it does not take into consideration what we call the hydrate depression effects, or the effects of, or what we call the reduction, or the hydrate depression effects due to the presence of large molecules. As a result, Trickle-Campbell method came and used the methane as a reference case, and use what we call the additive effects of other molecules to predict the hydrate point, which means that the presence of heavy molecules, for example, or large molecules, will cause what we call the hydrate depression effects. And this method is mainly about the hydrate depression effects due to the presence of other gaseous molecules or other hydrocarbon molecules. Let me put it this way. Pressure range for this method is between approximately 7 to 41 megapascal. And the method will require the use of 8 different charts that can be found also in the GBSA book as well, I guess. But I'm not going to present any of these charts. But you need to know that the Trickle-Campbell method deal with situation where you have large molecules and take into consideration these large molecules that may contribute to what we call the hydrate depression effects. And it can accommodate larger range of pressure between 7 to 41 megapascal. Meanwhile, the Katz method mainly operates at the pressure approximately 7 megapascal only. The third method, which is also accommodating for high pressure, or can be adjusted or used for high pressure system, is what we call the McLeod-Campbell method. The McLeod-Campbell method can be used for high pressure sweet gas, specifically between 35 and 40 megapascal. The method is based on what we call modified Clapeyron equation, and the data or the equation can be simplified in this form, where T is the hydrate temperature in Kelvin, equal to 2.16 C prime to the power 0.5, where C prime equal to the Ci multiplied by Xi dash. Where Ci is the component factor that we can see from the table in the next slide, and Xi is the mole fraction. Now, in the previous slides, we were exposed to what we called as the McLeod-Campbell method, which predict the hydrate temperature in Kelvin if you use the formula where T, or the hydrate formation temperature, is equal to 2.16 C prime to the power 0.5, and we said that we're going to calculate C prime, where C prime stands for the summation of Ci Xi prime. And the Ci is listed in the table here, where you can find that the C value, or the Ci, this is again similar to the Ci of the equation that you have seen it before. So the Ci is listed for a specific component, which is mainly C1, C2, C3, C4, and C4 isoputane and normal butane, which means that you are excluding all the heavier fraction. And as a result, you will get a new definition of what we call the Xi prime, which is the pseudo mole fraction. Because why we call it pseudo mole fraction? Because we are excluding from our calculation all the heavier fraction. So we are basing the mole fraction based on C1, C2, C3, IC4, and NC4, because these are the component that can be found or can be used to find, for example, the C value. So once you calculate how much is the Xi, which is the pseudo mole fraction for the component, how much, for example, is for C1, how much is for C2, C3, C4 I, or C4N, for example, you multiply the pseudo mole fraction multiplied by the Ci value for each component, and then you can calculate how much is the C prime. And once you get the C prime, you can calculate how much is the hydrate temperature. And as you can see here, we are getting the value of the C value, which is the C1, where the value of the C constant, or the Ci, or what we called before as Ci, in terms of pressure as well. So if you have the pressure equal to 41.4 and you have methane, for example, Ci will be equal to 18.9. sorry, 18,933. If you are dealing with higher pressure, let's say 96, then the C1 or the C value for the methane will be approximately 19,489. So using this method, you can calculate how much is the hydrate temperature in Kelvin. Now the fourth method that we can also use to predict the hydrate formation condition, which is like Bailey-Wishart method. Bailey-Wishart method normally will be used for sour gases, for the gases that include high concentration of CO2 and H2S as well. So the method is presented in the figure, or figure 2031 in the GBSA book, which can predict the hydrate temperature for the for the gases that has high content of H2S. The method is basically based on the principle of the adjusting or correlating the propane hydrate condition to account for the presence of H2S. And the method was developed based on the Bing-Robinson approach, or Bing-Robinson equation of state as well. So we're going to see in the next slide how do we use this chart, which is chart 2031. So as you can see, if you are dealing with low pressure system, sweet gas, you can use Cat's method. If you are dealing with more sophisticated scenario or higher pressure scenario, you can use the Campbell method or the McLeod-Campbell method. If you are dealing with situation where you have high concentration of CO2 and H2S, then you are dealing with, it's preferable to use the Bailey-Wishart method, which is represented in figure 2031 that I'm going to show it in the next slide in the GBSA book. And the method, as we mentioned earlier, is based on the fact that you are adjusting or correcting the propane hydrate condition, accounting for the presence of H2S or high percentage of H2S. And it's good to mention that this method is widely accepted, and it gives you a relatively accurate result. So now let's have a look at this example where we're gonna demonstrate the use of the Bailey-Wishart method, or the Bailey-Wishart chart, which is the for gases that has high concentration of sour gases such as H2S and CO2. So you have a gas stream, and this gas stream is at 4200 kilopascal and has a relative density of 0.682. The gas has also H2S content of approximately 4.18 H2S and C3 of approximately 0.67 mole percent respectively. So you need now to calculate how much is the hydrate temperature for this gas stream. So first of all, we're going to go for, since we are dealing with a gas stream that has high content of H2S and CO2, this means that we are dealing, or we have to use what we call the Bailey-Wishart method chart. And as you can see here, the chart is slightly complicated, where you can see the pressure here in kilopascal. These are the value for the pressure. For example, this is 40,000, 30,000, 10,000, 4,000, 3,000, 1,000 kilopascal, for example, absolute pressure. And in the x-axis you have the temperature, but the temperature is, as you can see, the temperature line is not vertical. So here, for example, the 30 is vertical, but here you have it inclined. Let me just change the color so you can see it better. So you have inclined value for temperature. So sometimes it's vertical, sometimes it's inclined, the temperature value. So you need to approximate. And you have also charts inside that represent the H2S content, which is, I'm going to draw it now in green, which is this value, or these charts that represent the H2S content. For example, this chart represents the 2%, this chart represents the 5%, this chart, for example, represents 10% H2S. So I'm going to use now, based on the data that I have, I'm going to see how can I obtain the sorry. So the hydrate temperature. And one more thing to keep in mind is the gas relative density, where the gas relative density represented here as horizontal line that I'm going to draw it now in red. So you can see how much piece of information you can use in this. So for example, this is approximately 0.8 specific gravity. So let me change the color because it's really hard to deal with the yellow one. Okay, so now I'm gonna go and I'm gonna do it step by step. First of all, what do we have piece of information? We have the pressure. How much is the pressure of the system? Is 42 100 kilopascal. So 4200 kilopascal. So I'm going to draw a horizontal line, which is the red line that you can see it here, and I'm going to dot it right now with blue. So this is the red line that you have. So this is the 4200 kilopascal. And I know that the concentration of H2S is approximately 4.18, which is slightly less than 5. So this is the line that has 5%. So I'm going to imagine that I have another line here that represents the 4.18, which is approximately here, or let's say 4. I'm going to draw another line similar to this, close to the 4. So once the red line hit the 4.18% H2S, I'm going to draw a vertical line, which is the green line, and I'm going to go down all the way. Let me just use different color. I'm going to go with the green line all the way down till I hit the value of the relative density, which is the relative density is equal to approximately how much? It's 0.682. So I'm going to go down all the way till it hit the value of 0.68, which is approximately here, you can see. Okay. So now I'm gonna draw a line that represents my temperature, but the line has to be inclined in the same way that the line before and after are inclined to. So I'm gonna draw a line here at the intersection between my pressure value, the H2S content value, all the way down vertically to the specific gravity value, and I'm going to draw this line that represents the temperature or the hydrate formation temperature, which is going to be around. So if I assume that this is 10, this is 20, so I'm going to assume that this is, for example, 12, this is 14, this is 6, this is like 12, this is like 14, this is like 16. So this will be between 16 and 20, so it could be around 18 or 17.8. So it could be around 18 degrees Celsius. So my hydrate formation temperature would be around 18 degrees Celsius. But in fact, I have high content of H2S sorry, and C3 or propane. So I need to adjust for the high concentration of the H2S. So I'm going to take the adjustment curve. I'm going to go now for the second curve, which is the adjustment curve, and I'm going to go for reading how can I do the adjustment from this curve. So I'm going to go first. I'm going to look at how much is the H2S content. I have H2S of 4.18, so which is approximately, so if this is 10, for example, approximately this is, let's assume that this is 10. In fact, this is approximately 10. So 4.18 is like a little bit below the 5. So this is my value. So I'm going to draw this blue line that you can see horizontally till it hit a curve. This curve, or what you are seeing here as domes, the chiclet domes, for example, these curves represent what we call the C3 content. Okay? And you can see here where you have 0%, here where you have 0.25%, for example, here 0.75%, here 0.9%. So I have the value of the C3 to be approximately 0.68, which is close to the 0.5, which is, it's not 0.75, so this is the 0.75, for example, and this is the 0.5, so it's somehow in between. So I'm going to imagine that I have a line here that represents the 0.68 value for me. And once of the CF3 adjustments, once the curve or once the horizontal line hit that point, I'm gonna go vertically down all the way with this green line that you can see. And this green line will go all the way down till it hit the pressure, because these values of 1, 5, 10 on the right side and the left side, these are the pressure value. And since the pressure is 4.2, so it's close to the 5. So I'm gonna imagine that I have another line here that represent the 4.2 value of the pressure. So once the vertical line hit that value of the pressure, I'm gonna go horizontally and read how much is the value or the correction. So you can imagine that this is 5, this is minus 5, sorry. So this should be minus 4, this should be minus 3, this should be minus 2, this should be minus 1. So I am somehow close to the minus 2, which is approximately to the minus 1.8, which means that I need to adjust the hydrate formation temperature by reducing 1.8, sorry. So this means that the adjusted value for the hydrate formation temperature will not be 17.8 that I calculated from this chart. I need to correct this one, and I need to take from that one 1.8 because in the negative value. If my reading goes to the right side here, okay, this means that I am in the positive side. This means that the hydrate formation temperature will be 17.8 plus, let's say, 1.5 or 1.2. But since we are dealing with the left side, this means that we are dealing with the negative value. This has to be subtracted from the value that I obtained earlier from the chart of the 17.8. I hope it's a good demonstration to look at this one. So please make sure you understand how do we draw, or how do we take the values, or how do we approximate or predict the value for the hydrate formation temperature using this technique. So it's very important for you to look at these values, or to understand how to obtain, and the step-by-step is listed here. The step-by-step technique is listed here. Again, this is like wood chart method, or Bailey wood chart method for the high content of CO2 and H2S. This is the clean chart where you, if you want to read more about the chart value and to look more clearly on the values of the, for example, H2S content, the pressure and temperature, because that one is a little bit crowded from the figures that we draw already. And finally, you can also use the what we call the equation of state principle, or we can use certain software or certain software packages that can also predict the hydrate formation condition in terms of pressure and temperature. The most common one is the CSMHYD, Equiphase, and Equilibrium software as well. These are example of software or simulation software that can be used also to predict the hydrate formation conditions.